Hello, this video follows up the one in the A-Level Physics Revision series on electromagnetism and responds to questions I've received about how eddy currents affect the electromagnetic flux in a core of a transformer. So let's just go back to basics and remind ourselves about what goes on. If you take a coil of wire, which is sometimes called a solenoid, and you pass a direct current, unchanging direct current, through that coil, then in the middle of the solenoid there will be a magnetic field. And the magnetic field strength, which is B, is equal to mu0, which is the permittivity of the permeability of free space, multiplied by the current that's going through the wire, multiplied by the number of turns in the solenoid. So you can see from that if you change the current, you change the magnetic field. If the current is steady, then the magnetic field will be steady. If on the other hand you have exactly the same setup, but this time instead of using a battery to generate a direct current and an unchanging one, this time you have an alternating current source, then what will happen is that the current, if we measure the current in this direction multiplied by time in this direction, then that will almost certainly be a sine wave if you use ordinary alternating current. Which means that the value of the current at any point in time is constantly going up and down in a sine wave form. And so there is a constantly changing current. It will have a form I equals I naught, where I naught is the maximum value, times sine omega t, where omega is 2 pi f, and f is the frequency of the wave, which is the number of times a crest passes a particular point in 1 second. And that will therefore have a varying current because it's constantly going up and down. And if you have a varying current, then according to this, you will have a varying magnetic field. Now, what has all that got to do with it? Well, Faraday says that as far as induced EMFs and induced currents are concerned, if you have a steady current and thus a steady magnetic field, you don't get any induction at all, because Faraday says that an induced EMF is equal to flux change divided by time, which is usually written d phi by dt. Now if you've got a constant magnetic flux, then there isn't a flux change, so there will be no induced EMF. So if you have this arrangement here, where you have your solenoid or your coil of wire, an alternating generating an alternating voltage which produces an alternating current, then you will get a variation in the magnetic field. And that means that if you bring another coil, and this time we'll just put a voltmeter here, so there's no power supply in this at all, we're simply registering what happens, then Faraday's law says that where you have a changing magnetic field, you can have an induced EMF and thus an induced current in this circuit. And which way will the current flow? Well, that's where we have to go to Lenz's law, because Lenz's law says that the current will always flow in the direction such that it opposes the change that caused it. And what that basically means is if the current is generated by a magnetic field in that direction, that will be a changing magnetic field in that direction, so you've got this rate of change here, then the current will flow in such a way as to create a magnetic field in that direction, opposite to the one that caused it. That's what Lenz's law says. By contrast, if you were to bring that self-same coil, that's this coil here, this circuit here, if you were to bring that next to this circuit, then no current would be induced in the second circuit at all, because there's no changing magnetic field. So let's just have a look and see what we mean. Let's take a single coil of wire which will make rectangular in shape, and underneath it we have a magnet, north-south. If we just leave that magnet there, no current flows in this loop because there is no changing magnetic field. There will of course be a magnetic field going from north to south, and it'll continue right the way around here, but there's no change in it, therefore no current flows. But if you were now to take that magnet and move it up through the centre of this loop, then you've got a changing magnetic field, and as a consequence you'll find that a current will flow in the wire. And in my series on electromagnetism I taught how to work out which direction the current would flow. We won't worry too much about which direction because that you can work out. The key thing is that how do we know which direction the current will flow? Well, it will flow in such a way that it will produce a magnetic field in the opposite direction to this magnetic field. So the current will flow in the direction that it needs to flow in order to, as it were, counter the magnetic field that's moving up through the cable. Now, what we said with transformers was that if you take a coil with a certain number of turns, say N1 turns, and you have well actually we'll call that NP terms and VP volts. So the voltage supply is V, and the P stands for primary, and the number of turns is N in the primary. And you then have another circuit with N, which is the secondary circuit, with NS, that's the number in the secondary, and you want to know what will the voltage in the secondary be. Then we developed in the video on electromagnetism the formula that Vp equals Np dphi by dt, where dphi by dt is the change of flux caused by this alternating voltage. And we also said that Vs is Ns dphi by dt. It's the same rate of change of flux because both of these solenoids are experiencing the same rate of change of flux. And from that you get that Vp divided by Vs equals Np divided by Ns. So in other words, if you have Np has 100 turns and Ns has 50 turns, then Vp will, so the Np over Ns is 2, then Vp over Vs will be 2. So whatever your voltage is for in the primary, you'll get half of that in the secondary. So you can either step up or step down the voltage, and we explained this in the video, depending on how many turns you have. If you have fewer turns, then you get a smaller voltage. If you have more turns than the primary, you get a higher voltage. So you can step up or step down as the case may be. But you have a problem if you do it like this, because whilst in theory the rate of change of flux is the same in both cases, don't forget that the magnetic field is actually being created in the middle of the solenoid here. Once it gets outside the solenoid, once it gets into this region, and indeed in this region, the magnetic field that is varying inside the solenoid is going to be quite different once it gets outside, and it's very much more difficult and complex to describe. So the idea that these two rates of change of flux are the same is actually theoretically true, but in practice it isn't, because the rate of change of flux inside the solenoid is quite different from the rate of change of flux outside the solenoid applying to this coil here. So the way people get round that as a problem is they put the coils around a what's called core, and it's usually made of something like iron, some kind of ferrous material. So here we have an iron core, and you put the first solenoid round that one, and you put the second solenoid round that one, and this is then the primary, and this is the number of turns in the secondary, and the same principle as we had up here applies. But why does this work? Well, what happens is that you get a magnetic field in the primary, because this has got an alternating current, alternating voltage attached to it. Once you have a magnetic field in the primary, then that magnetic field will magnetize the iron core. And once the atoms in the iron core inside the solenoid are magnetized, then they will have a magnetic effect on all the atoms right the way around. So in fact, effectively the iron core carries the magnetization right the way around, and you have the same magnetization, and indeed changing magnetization, because this field is constantly changing backwards and forwards, and so that's going to have the same effect in the core, so that you get broadly the same change of magnetic flux on this side, and therefore these two are broadly equal, and thus this formula does hold true. And what we said in the video on electromagnetism was that in theory, the power from this side should equal the power from that side. And power, don't forget, in electrical terms is always V times I. So what you would say is that the voltage in the primary times the current in the primary is equal to the voltage in the secondary times the current in the secondary. And that, if that were true, would suggest that the transformer was 100% efficient, because you've got a transfer of power. Exactly, the power in equals the power out. But that isn't true, of course. It's very rarely true in anything. You lose some form of power, and you can lose it by a variety of ways. This video considers why you lose it through eddy currents in this iron core. Well, let me just start by having a little experiment. Here's a magnet. I'm going to have the south and the north, so the field lines are going from north to south. And what I'm going to do is I'm going to have a kind of pendulum, which is going to swing backwards and forwards through the magnetic field. Except instead of putting a bob on the end of my pendulum, I'm going to have a metal plate. So it's just a thin metal disc. Now, what happens as I let that pendulum swing through the magnetic field? Well, imagine it was a wire. We know that if you have a magnetic, here's a magnet north, south, and here's a wire. If you move that wire down quickly, that will induce a current to flow in the wire. Well, exactly the same thing happens here. As the metallic disc goes through the magnetic field, it will induce a current. But unlike a wire where the current flows along the wire, this is a metal disc. So what you actually get is an eddy current. A little current flows on the surface of the disc. And how do we know which direction that eddy current flows? Well, Lenz's law tells us. It flows in a direction such as to oppose the magnetic field that creates it. So if the magnetic field is moving from north to south upwards, then the current will flow in the disc in such a way as to create a magnetic field downwards to oppose this one here. But if a current flows, then we know that in terms of power is V times I. We just did that up here. So, and V equals to IR, so if V equals IR, then the power is equal to I squared R. There's going to be some resistance in this metal disc. So there is going to be a power loss as this disc goes through the magnetic field. And it's achieved through heating up. As that little disc goes through the magnetic field, the current flows and it will warm up. And so you lose power. And what happens when you lose power? What happens is as the disc goes through, it slows down. It's actually called magnetic braking. This is a way in which braking can be achieved. You have a disc going through a magnetic field. Instead of just swinging backwards and forwards like a pendulum might, it swings and then it goes very, very slowly. It probably doesn't come out. It just stops. It's a braking system. And the reason it brakes is because you've got this eddy current creating a magnetic field in the opposite direction to this magnetic field, generating heat and losing power, and the whole thing breaks this pendulum. Well, you can see what's going to happen here. You have a magnetic field generated by this solenoid, and that magnetic field and that is a changing magnetic field. So that magnetic field is going to induce eddy currents in this iron core. The iron core is good because it transmits the magnetic field, but it's bad because it will have induced eddy currents in the core as well as in the secondary solenoid. And those eddy currents will have a size, and there will also be a resistance in the core, so they too will have a power loss. And that power loss has to come from somewhere, and it has to come out of this power in. So if you lose some power through the eddy currents in the core, you're not going to have as much power in the secondary, and that's why you get, well, it's one of the reasons why you get power losses in a transformer, and why the transformer isn't 100% efficient. The way to solve this problem, or partially to solve it at any rate, is to make the iron core made of layers of iron separated by insulating material. So if you make your iron core like that and then wrap your coil around it, now because you've got iron and then insulator, iron then insulator, that's fine as far as transmitting the magnetic field is concerned, because these iron layers will become magnetized and will cause the layers below to become magnetized, and therefore will transmit the magnetic field. But now, given that the magnetic field created by this primary will say be in that direction, it's of course changing, the eddies will flow in such a way as to cause the magnetic field to oppose it, but no current can flow downwards, because of course it's not going to get very far before it gets to a piece of insulating material. And so consequently you can restrict the extent of the eddy currents that are flowing by having layers of iron separated by insulating material, but you can never stop the eddies altogether. They will flow in the layers, they just can't flow between the layers. So this is a way of reducing but not eliminating power loss in a transformer.